some of these old guys were really clever. And so this is kind of just a pipe, an organ pipe, any kind of a pipe, just an empty pipe with both ends free. And inside there's a wire mesh, you know, just a wire mesh that you have on top of Bunsen burner stands sometimes. And what I'll do is I'll raise this up, and maybe you can help with that, and then I'll try to heat up the wire mesh. And an interesting thing will happen if everything is good. This is tight enough. Let's see. The main thing is that I have to.
And do you want it to fall verify?
No, about here. I just don't want it to fall down. Maybe you could kind of hold it here. Put your hand here so it doesn't fall. No, put your hand here.
Don't worry, he's only going to get it hot.
maybe let's use
Copper's not a good conductor of heat, so.
We can try it.
Main thing is I don't want it to fall down. Because I'll be down there. Okay. It's okay.
There's a wet wire mesh.
This nozzle isn't very good. Okay, so the experimental physics always complicated. So there's this wire mesh in here. I'm going to go in there and I'm going to heat up the wire mesh. Okay, that's all. I'm going to just stick the flame up there and the wire mesh will get hot. That's all.
Don't let it fall on me, whatever. Okay, so the bottom is kind of near where the wire mesh is. Okay.
That's all. The wire mesh is not in the right place. If you play with it and get the wire mesh in the right place, which is about a third of the way, it makes a very loud sound.
It needs to be an anti-node.
That's the 1/3 of the height?
Yeah, not exactly, but approximately a third of the position.
Seconds, it's
So-
an anti-node there.
No,
There
I mean you know, it's a usual thing. The pressure is a maximum minimum in the middle, and it's atmospheric at both ends. And what happens is that the air is kind of vibrating like this, and because it's hot, it's also translating. And so if things conspire to be such that the compressed air ends up sort of stuck, so because the motion, right, if you think of, you have this kind of oscillating motion and translation upwards, the air is spending more time in certain places than others. And when the compressed air spends time near the hot mesh, then its pressure goes up even more. So that's how you're pumping energy into the oscillating mode. So it's really beautiful, but it's not quite right because it's usually very loud. You can hear the windows shake. Okay. So you can, if you want to play with it later, you can, provided you don't kill yourself. But as I just wanted to show you this, and it's a very beautiful thing. It's a kind of an acoustic laser. You're applying DC energy to it, just a warm thing, and it makes this really beautiful sound. I'd like to make an electric heater there, so you can just push a button and it will heat up. Sounds very, very loud. Okay, so it's interesting physics. All right, so we're calculating cos theta that way. And so we have this integral where we have, and I'm just going to replace cos theta by x, just to make life simple. So here we have an x, and then we have the Taylor series expansion. which is 1, plus, now we have to put in here all the terms that we have up in the Boltzmann factor. So we have mu e over kt times x, right? That's the first term. The second term is plus alpha e squared over 2kt x squared. Okay, so this is the first term in the Taylor series expansion. Now we have to decide how far we should go. You know, at some point we should truncate this story, right? Well, it's good to go to order x squared. Why not? We want to keep this polarizability contribution. So if I want to stop at x squared, I have to look at the next term, because there will be a square term in there. There will also be higher order terms, but we won't consider those. So the next term that we'll have will be plus 1/2, and everything inside there squared, and the guy that we'll get is mu squared e squared kt squared times x squared. And then all the other terms will be higher order terms. We'll get an x cubed term from the cross product. So we'll stop here, even though this continues, and then we have dx, and we go from -1 to 1, and then we have the denominator, which is just the same, but we don't have the x. So we have 1 plus this stuff, dx. All right, so we already know that if we just keep this term, it's the same as no electric field, we get 0. But if we keep this term, then we'll have something. So, but first let's look at the denominator. So here, this next term is going to be much smaller than this term, so we throw it away. So the denominator will just be 2, like before. Now here, I cannot just throw these terms away, because this term will just give me 0. So I have to keep the terms that don't give me 0. So we go to this term, and then we'll just have an x squared. So we'll have mu e over kt times x squared, which will be we integrated 1/3 x cubed, and then we'll get a 2 from putting in the limits, and we have a 2 on the bottom, so we'll just get 1/3. So that's the first part that we get. And then the next term that we get will be x cubed. And that will be 0, because it's odd. So this will be the leading term that we get, and that's good. All right. Then, let's look at the co-squared guy, see how big that is. So the point is that now, if you know how big the dipole moment is, how big the electric field is, how big kT is, you can say how well this molecule will align. That's an interesting thing. You know, if you put an electric field on something, glass of water, you put a battery across it, how well will these molecules align? Basically, it's given by this. This guy here, same story, -1 to 1. We have x squared, 1 plus mu e over kt x, and then we can collect these other terms, alpha e squared over 2kt plus 1/2 mu squared e squared over kt squared times x squared dx, and the denominator we know is just going to be 2. Okay, well this guy just gives us a 1/3, which we know. Right? What about this guy? X squared. No, sorry. This will give us a 1/3. What about this guy? X cubed. 0, right? Because these guys are going to be cancel out. And so then here we'll have a term, so we'll have 1/3 coming from here, nothing from here. And then the next guy we get is from here, so we'll have all these coefficients, alpha e squared over 2kt plus 1/2 mu squared e squared over kt squared. And then we have 1/5 x to the 5th. You put in the limits, you're going to get 2. X to the 5th is this, x to the minus 1 to the 5th is minus 1. You subtract it, you get 2. And we have 2 in the denominator, so that cancels out. So we just get a 5th here. That's it. So we can figure out then to what extent the molecules align in an electric field. So let's try to estimate, just to see, what is this? So now what is mu typically? It's kind of hard to know that, right? But you can sort of think, I mean, what do we have? Molecule, after all, has nuclei with protons and neutrons and then electrons, and it's electrically neutral. And so why do we have a dipole moment? Well, an electron goes somewhere from its equilibrium position. So typically the charge that's displaced is like an electron, and the distance is displaced is how much?
The length of the molecule.
Yeah, that would be that would be kind of a maximum. Yeah. So a very crude estimate is 1 electron, charge of 1 electron times 1 atomic radius. Now, what's 1 electron? 0.6 10 to the minus 19 coulombs. And what is an atomic radius? Bohr radius? 10, well, yeah, a Bohr radius is 0.53 times 10 to the minus 10. So 10 to the minus 10. Right, so typically, I would say it's 1/2, right? 10 to the minus 10. And so basically this is 10 to the minus 29 coulomb meter. Right? Now that's a pretty big dipole.
Where is 1/2?
Hmm?
Where does 1/2 come from?
Oh, the size of a hydrogen atom. Hydrogen atom is 0.53 angstroms. That's the Bohr radius. Hydrogen, right?
Okay.
Plus charge, electron, that's the Bohr radius, 0.53 times 10 to the minus 10.
Okay.
So that just to get a kind of a measure of that length scale. And I never remember this because I don't like to use these units, but I have in the notes something that a debye, 1 debye, chemists like this unit. It's named after the chemist Peter Debye, is, for some strange reason, using static rules and stuff. It ends up in 3.33 times 10 to the minus 30th coulomb meter. So so 33 times 10 to the, I want to make sure I get this right, 0.33. 0.33 times 10 to the minus 29 coulomb meter. So So a dipole is less than this, right? And typically, dipole moments are some fraction of a dipole, half a dipole or something like that. So this is a large dipole moment. Okay, so typically, you expect something smaller than that. But let's suppose that that's what we have. Now, what is the biggest electric field that we can imagine? 10 to the 7 volts per meter, yeah. If you try to make a big electric field, of course, what happens is you have a spark. Boom, things are gone. If you just take 2 wires and you bring them close together, there's a very big electric field in there, and some wandering air molecule goes inside. The electrons get pulled one way, the nucleus the other way, and it comes apart. When it comes apart, when you ionize that molecule, the electrons accelerate one way, nucleus the other way, they crash into other molecules, makes it easier for them to come apart, so they come apart, and you have a spark, you have current. And so typically in dry air, depending on the electrodes that you have, but you can get up to about 10 to the 7 volts per meter, not much more than that. Now, it's good to think about liquid crystal cells. Typically the voltages you apply, maybe 1 volt or 3 volts or something. We use dimensional analysis to calculate the critical voltage for a liquid crystal cell. We said it was something like 1 volt. Did you do that or not? Just imagine.
I was in the hobo.
Yeah. So it's order 1 volt. So you kind of have to apply a volt or 2 to typical liquid crystal displays. But the distances are really small. So if the separation is 1 micron, then the electric field, 1 volt per micron is 10 to the 6 volts per meter. So although these are really, this is a huge field, we have comparable fields in here, with small voltages, because the distances are really small. Okay, so we were talking about what happens in this gas, so we somehow made this big field. And you can actually get transformers. For neon lights, you have transformers that make very high voltages, thousands, 50,000 to 30,000 volts per meter. You get the electrodes close together to get these fields. So let's see what degree of alignment we have now that we know the numbers. So this is approximately 10 to the minus 29. The electric field is 10 to the 7, and then we have a 3, and then we have a K, which is, what's K Boltzmann's constant? 1.38 times 10 to the minus 23. So that's the key number is the exponent. And then temperature, suppose your room temperature is about 300 Kelvin. So we get this. So this is roughly 4 then, and we have 4 times 3, well that's about 10. So here we have 1,000. So this is 10 to the minus 20th. Comes up, becomes plus 20th. So we have 10 to the minus 9, 10 to the 7. 10 to the minus 2. So even if you have a huge dipole, 1 electron moving 1 Bohr radius, the average value of cos theta is really, really small. So if you just have individual molecules and you put even a huge electric field on them, you hardly align them, even though you may have a huge walloping dipole moment for the moment. And that is just because the energy of interaction, the electrical dipole electric field interaction energy, is just a lot smaller than kT. KT just keeps agitating the molecules, even though they like the electric field. KT just kicks the daylights out of them and they point everywhere. Okay, suppose that you have a molecule with no dipole. Put that in an electric field, what happens? Okay, well we have this 1/3, and we know that an isotropic distribution will give us this. So this is the interesting part here. And let's see what we get here. Well, we already know what happens here, because we just calculated this guy. This is about 10 to the minus 2. So this will be the order of 10 to the minus 4. But if we have no electric dipole, we need to calculate this guy. And we need to figure out what this is. So then the question is, how big is alpha? Who knows? Let's do dimensional analysis. Later we'll do it properly, but let's just say, okay, we don't know anything. Let's see if we can figure out what alpha is in dimensional analysis. Okay, what do we know? We know something like this. We know that the dipole moment is proportional to the electric field. That's a definition of alpha. We're going to start somewhere. Now we're going to figure out, I mean, we know the units here and the units there, right? So in principle, we can figure out what the units of alpha are. Now I want to make things a little easier, so I want to cheat a little bit. Let me multiply through by an electric field. Now I have PE equals alpha E squared. This is good. But PE has units of
Energy.
energy, yeah. It's true that KT is energy, right? But yeah, just energy. This is units of energy. That's good. But this doesn't have units of energy. I'd like it to have units of energy, then I wouldn't have to worry about
QE is equal to energy.
QE
Yeah.
is equal to energy.
Force.
But what is the energy density of the electric field? If I have a box and it is uniform electric,
epsilon 0.
yes?
Yeah. Epsilon 0 multiply E square.
E squared, yes. Epsilon naught E squared. Right. So energy density is epsilon naught times E squared. So I'm going to multiply by epsilon naught and divide by epsilon naught. And then I have energy here. I have energy here. I have energy per volume here. That means this guy must have units of volume. Right? So alpha must have units of epsilon naught times volume. So dimensional analysis says that this has units of epsilon naught times volume. Okay, good. Okay, everybody's happy? So there's dimensional analysis. And again, I want to show you guys that this is really useful stuff. You don't have to worry about solving Maxwell's equation for some complicated thing. Okay, so then you say, okay, I have, let's say, an atom, some spherical guy. I need to figure out its polarizability. Well, it's epsilon naught times the volume. What volume do I have? Yeah, that's all I have. The only thing I have is an atom, so the volume must be the volume of the atom, volume of the molecule. And in fact, if you do this, and we will do this soon, it's just going to be that. It'll turn out as a factor of 3, but that's what the polarizability is. See, it's really beautiful. You can get these nice results just by thinking about units. Okay, so now we can estimate what alpha is. We just stick in 4/3 pi r cubed for our atom. So okay, so let's go. So what's epsilon naught? Lift epsilon.
I don't know off the top of my head.
That's what you have to know. Right? I mean, the things we need to know are just the simple things. C, U naught, epsilon naught, times constant K. Just a who knows what it is? Oh, push. Yeah.
8.85 turn minus, turn 26.
10 to the minus.
26.
Better to remember the exponent than not the So yeah, it's 8.85 times 10 to the minus 12.
12.
What's mu now?
4.8 minus
Yeah, that's easier at 4 pi. Okay,
It's
so
not.
8.85 times 10 to the minus 12 is kind of the same as 10 to the minus 11, right? So this is about 10 to the minus 11. And then what's the molecular volume? The 4/3 pi is just 4.
10 minus
So
30.
it's 4 times r cubed. Well, what's r? I don't know.
And
Maybe
you
half,
have
half an angstrom. or something. So 1/8, 10 to the minus 30. And so what you see here, that this alpha is really small, right? So it's the order of 10 to the minus 41. It's really small. And now the beauty is that if you now start to do experiments, measure molecular polarizabilities, you get numbers in this category. So you can get the order of magnitude right away, and then it takes you a year to get one more digit, 2 years to get 2 more digits. All right. Lejeune was a master of it. Lejeune could just look at something and estimate things and get out the numbers that you needed to get a sense of where the problem is going. Okay, so we're interested in this, alpha e squared over kt. So alpha e squared over kt. Forget about all these other things. We have 10 to the minus 41. We have e squared, 10 to the 14. We have kt, 1.38 times 10 to the minus 23. Then we have 300. So here we have something like 400 here. Let's say it's 1,000. Then this is 10 to the minus 20th. It comes up and it becomes 10 to the plus 20th. So we have 10 to the 34 minus 41. This is 10 to the minus 7. Nothing, right? So if you only have a polarizable molecule, there's just hardly any alignment by the electric field at all. So if you want to align molecules, you really need a dipole moment. And even then, you don't get very far. Okay, so this guy is going to be really small, and it's dominated by the dipole moment. So this is 10 to the minus 7, and this guy is 10 to the minus 4. But if you have no dipole, lots of molecules have no dipole moment, then all you're left with is this guy, it's really, really small. So now there's a fundamental question. If this is true, that these energies are small compared to kT, and I can't align molecules with an electric field, then how come I displace one? I'm applying an electric field. Yeah, you see things changing. So there's some discrepancy here. We just showed what you can't do.
That means that molecules want to align themselves, but with electric field you just change the preferred direction of the alignment.
The director.
And powerlessness.
Yeah, it's kind of like that.
But it's small to change the sort of order of the system, the total order, but it's enough to change the some direction.
because
So-
when the words react forces, they are coupled together.
Yeah, so the answer lies in that. The answer lies in cooperative behavior. That we're talking about an ideal gas of non-interacting particles. Individual molecule in an electric field, doesn't matter how long it is not going to align at room temperature. cool it down to absolute zero, close to it, maybe you can do something, but generally you can't do. But if you get a bunch of them together, it turns out that you can do it. And that's the whole secret of displays. And how does that work? Well, suppose that you take two molecules and you glue them together somehow, mysteriously. Maybe van der Waals forces, maybe something else, but somehow you put them together. Now, these two things are like one molecule, but they have twice the dipole moment. So this mu becomes 2, but KT is still just KT. So if you can get a whole bunch of molecules to stick together, then you can make both mu huge and alpha huge, right? The volume is going to get huge. And KT will just still be KT. So this is how cooperative phenomena can overcome the disordering effect of KT. Okay. So, all right. I already have done before. So we'll stop here.